Hello and welcome. Today we're going to finish out and do more of the whys of the Laplace transform. So this is really part two of two videos on the introduction of Laplace transforms. And I wanted to talk a bit more about the Laplace transform and its properties, some of the more technical details of what this is, and some of the math that's related to it. So first, let's get the definition down again. It's f of t e to the negative st dt, okay, like that, right? And that's equal to this function here, and this is what we call the transform to the frequency domain representation of f of t. And what's really important here is the idea that these transforms are unique, right? The idea here is that if LF exists, and that means that the integral itself exists for values of s, then there is a unique f of s that corresponds to it, i.e. I can write that like that. And also, given f of s, there is a unique f of t such that the inverse Laplace transform of f of s, capital F of s, corresponds to that f of t. And what's really important, though, is to understand that this only is true if this Laplace transform exists in the first place. All right, and that means that that we have to have this thing existing. Okay, so another little ground rule here is that f of t has a domain. So the domain is going to be t greater than or equal to 0. Okay, that's going to be the domain here. Obviously, when we're integrating the Laplace transform, that's the domain that we're integrating on. And this is actually useful for initial value problems because typically, we want to know what happens. We have initial data, x of t of 0 is equal to x0, and we want to know what happens in the future, x of t, right? So that initial data corresponds nicely to the domain the functions that we're dealing with are on. Okay, right, so that's one property, the idea that there's this one-to-one correspondence. If I have an f of t there, I can map it with this Laplace transform to get f of s. And if I have an f of s, I can apply the inverse operator to get back to f of t. And there's a one-to-one correspondence between those two things, provided the function in question has a Laplace transform. Okay, so now let's talk about another property of the transform. So the properties of the Laplace transform or operator. The really important one is linearity. Linearity, and this means it plays nice with vector spaces of functions. So if I have Laplace transform and I want to take the transform of a times f of t plus b times g of t, where a and b are constants, okay, then that can be written as a times Laplace transform of f plus b times Laplace transform of g. And this linearity is a direct result of the linearity of integrals. And it should be noted, of course, that we always have that hypothesis that it has to be true that these two things exist. That's the only way we can have that computation make any sense. But the fact that scalars pass through the transform is also very useful. Okay. A couple of other properties that are fairly interesting here. So this linearity property allows us to do some neat things. The other thing that we like to do is, now I just want to give you some examples transforms. Okay, so example transforms. So we did in the previous video that this is equal to 1 over s. Laplace transform of t to the first power is equal to 1 over s squared, and Laplace transform of t to the n is equal to n factorial all over s to the n plus 1. All right, so those were pretty neat, but we wanted to do some other ones now. Okay, so I want to do now Laplace transform of e to the rt, one of our favorite functions. All right, and of course we can do that straightforwardly. E to the rt, e to the negative st dt. We can combine the product of two exponentials of the same base is the exponential with the sum of the exponents. Okay, and so we can write that as r minus s of t dt, like so. And then, of course, we can take the antiderivative of that straightforwardly. But we have to now put a minus sign there, and then e to the r minus s t, like that. Okay. Actually, hold on. I'm being a little bit, I'm getting a little ahead of myself. It's simply that, right there. We're not putting a minus sign there. And we have to go 0 to infinity. But here, for us to get an answer, we need to have, again, another asterisk here. We have to figure out, so r minus s has to be greater than 0. Remember, s and r are both constants. And for this, oops, I'm sorry. I'm bad again. This has to be less than 0, right? It has to be less than 0. So, so e to the r minus t, rs minus s times t decays. Okay. All right. So, presuming that's true, what we're going to end up with is, of course, 1 over s minus r sitting right there. So that is the Laplace transform of an exponential, but we have to put that that proviso, though, that r is less than s, or rather that s has to be strictly greater than r in order for that to exist. So here's an example of a Laplace transform where for the s's domain is going to be a little bit more interesting. All right, let's go to the next slide here. Okay, and now I'm not going to compute all these otherwise, but what I want to do is actually just list off some of these ones that you should probably commit to memory. The Laplace transform of sine of omega t, right? So when we convert to frequency space, this has a really nice result. It's going to be omega all over s squared plus omega squared. So that's really nice. And of course, the limit on the domain of S has to be greater than 0. But do you note here also, I'm going to put another asterisk, S is a frequency units. And omega is, of course, also in frequency units. And so, of course, we can sum the two of the same units together, the squares, like that. So again, this just underscores the fact that when we do this transform, the capital F is a correspondence of our little f, our sign, but in the frequency domain. So there's a corresponding very similar cosine omega t transform. And that's going to be capital F of S again. And one can do the calculation pretty straightforwardly, but I'll just leave it for you guys to do. I'll just list off the result. Is going to be S over S squared plus omega squared, just like before. All right, and I said before that that L is useful for discontinuous functions. Or functions with jump-tust continuities. So I thought we might do one. Okay, I'm going to call h of t, it's what I call the Heaviside. That's actually a capital H because it's a person's name. The Heaviside function, and its h of t is equal to the piecewise function. It's equal to 0 when t is less than 0, and 1 when t is greater than or equal to 0. That is one of the definitions. Also, h of t minus a is just, all this is a right shift. And that's simply equal to 0 if t is less than a, and 1 when t is greater than or equal to a. Okay, so the graph of this function just looks like this at a, and then it jumps up to 1 and goes like that. All right, so that's the graph of that Heaviside function. Well, let's see if we can compute it. Laplace transform of capital H t minus a is going to equal the integral from 0 to infinity of h of t minus a e to the negative st dt. What I really want to do is actually do a u substitution. So I'm going to actually substitute u is equal to t minus a. Okay, and that's because, of course, this function, this is actually equal to the integral from a to infinity of 1 e to the negative st. All right, so actually maybe I won't even do the u substitution. I can just go with this. All right, because every t value prior to a, the function is simply 0 anyway. So we could compute this pretty straightforwardly. That's 1 over s negative e to the negative st. And now we're going to evaluate at a and infinity like that. And we're going to end up with e to the negative s times a all over s. Okay. All right, so that's the Laplace transform of the Heaviside. Okay. So those are some very nice results that I wanted to show you about the Laplace transform. Not much more to do there in terms of definitions. I think we've got most of the ground rules for a Laplace transform now. All right, so I'll leave it at that.